Now, many of you will have learned titration in high school, and you'll have been taught a formula which is very easy to use and is perfect for high school problems. And you may notice that I gave a much longer-winded answer in the last clip, one based on diagrams. And the reason for that is, while that formula is very easy to use in high school problems, the method, the idea of the method that I used in the last clip is much more generalizable to the actual type of problem that you're going to face in Chem 2070. And so here's the kind of problem that you probably will not have seen in high school, but you could easily see in Chem 2070, which is the following. How many mils of a 0.63 molar BaOH2 solution are needed to be added to 31.8 mils of a 0.751 pH HNO3 solution to make a solution with a final pH of 0.91. And first we notice that HNO3 is a strong acid, so it's good for 2070, and BaOH2 is a strong base, and both of these make in stoichiometric amounts H plus and OH minus. So BaOH2 solid goes to Ba2 plus aqueous plus 2 OH minus aqueous. So for every mole of BOH, we get 2 moles of OH minus, and HNO3 nitric acid goes to H plus aqueous plus NO3 minus aqueous. Okay, now this is a harder problem that you will see in high school most probably, and the complication is that is this actually a titration? In titration, you have exactly the same amount of acid and base. And when you have exactly the same amount of acid and base, the amount of acid and base is equal, strong acid and strong base is equal, which means that you will end up with a neutral solution, because a neutral solution has as much acid and base. So is this problem a typical titration problem? Put it in chat. Read the problem, decide if this is a typical titration problem at the equivalence point. Put that in chat. So the key is that the final pH is 0.91, which is acidic. And that means that we didn't have the same amount of acid and base. In fact, if it's acidic, we must have had more acid. So if this is not a titration problem, what kind of problem is this really? Put it in chat. Remember, in titration, we have exactly the same amount of acid and base. Here we don't. What kind of problem is this really? Put it in chat. Good. This is a limiting reactant problem. And if it's a limiting reactant problem, what is the best way for us to treat it? What diagram should we use? Put it in chat. Put it in chat. Good. We will need an ice table. The reaction is still H plus OH minus going to H2O, but we will need an ice table. Okay, so what are our data? We have, let's divide it up. We have the initial acid. We have the initial base. And then we have the final solution. And in this problem, do we know more about the acid or the base at the beginning? Put in chat, which do we know more about? The acid, the initial acid, or the initial base? Yes, we have both the volume and the pH of the acid, and so we know that the H plus concentration is 10 to the minus 0.751 molar, which is equal to 0.1774 molar. Ooh, sorry, I should change the words here. This is, we know about the initial acid solution, so I'll write acid here, and I'll write base here. And we also know the volume, it's 31.8 milliliters, which is 0.0318 liters. And so we can get the moles is, moles of H plus is equal to 0.1774 times 0.0318, and that's equal to 0.00563 moles. And we enter that right here. Okay, now we know less about the base solution. We know that we have 0.63 molar BaOH2. For every 1 BaOH2 we make, according to this reaction right here, for every 1 BaOH2 we make 2 OH minuses, so the OH minus concentration is the double, 0.126 molar, and the unknown is its volume, the volume of the BaOH2, which I'll just abbreviate as V. Okay, so molar is in moles per liter. And so if I want the number of moles of OH minus, it's going to be 0.126 V. And I'll put that in here. And now we have the final solution. The final solution has a pH of 0.91. Is that an acidic solution or a basic solution? Remember, 7 is the pH, which is the neutral solution. 4, the acidic solution. 4, pH of 10, the basic solution. pH of 0.91, is it acidic or basic? Put it in chat. If it's less than 7, it is acidic, which means that we're going to have a lot more of H plus than OH minus. And the, what will it be? The final pH, the H plus concentration, remember it's just zillions of times more. The H plus concentration is 10, it's minus 0.91, and that makes it 0.123 molar when you plug in the calculator. And now the question is, what is the volume? And this is the point. Write in chat the volume of the final solution. Write in chat the volume of the final solution. Good. It's going to be the sum of the two volumes, which is 0.0318 plus V, the initial volume of the BaOH2 solution. And so the final concentration of a number of moles of H plus, this is in liters, this is in moles per liter, and the number of moles then will be the product of the two, 0.123 times 0.0318 plus V. And that's the number of moles of H plus. And tell me, where do I enter that into the ICE table? Tell me where I enter it. In which line? I, C, or E? Put it in chat. Good, you put it into E. So it's 0.123 times 0.0318 plus V. And is there a lot, millions or billions, or maybe even tens of billions times more H plus or OH minus? pH is very low, close to 1. There are, yes, a trillion times more H plus than OH minus. The amount of OH minus is essentially 0. So this is a limit reactant problem. It got all used up. And that means that the change in OH minus is minus 0.126 because in the change line, the values are an exact ratio of the coefficients, which are 1 to 1. There are, put how many moles, I'll just put it down. There's minus 0.126 moles of H plus used up. And now we can write an equation. 0.00563. Oh, sorry. I forgot. It's not minus 0.126, minus 1.6 V. That's very important. So let me look at that V. Sorry about that mistake. Minus 0.126 V. So 0.00563 minus 0.126 V equals 0.123 times 0.0318 plus V. There is one equation and one variable. We can solve for V. And if you do that, you get V equals 0.00124 liters, which is equal to 1.24 milliliters. And that's the answer. And I think you can see why you want to use the diagram and the ice table methods for our strong acid and strong base problems, and not the kind of formula that you probably were taught in high school.